So, the idea behind an amplifier is to get gain, that is, you have some input signal and you want to get a modified or magnified version of it at the output. Okay. Now, no device will give you power gain, that is, the output power cannot be more than the input power. But what our active devices do is that they give you incremental power gain, that is, if you bias them around a certain operating point, it is possible to get a larger increment in the output power than the increment in the input power. The output power can never be larger than the input power, because such a thing would be a generator. Now, we do not have any power generators on our devices, right. So, it can only consume power, it will dissipate power, but if you have a nonlinear device and if you arrange it in the right kind of environment, I mean the right kind of biasing, then small increment in the input power and a larger increment in the output power. Okay. Now, we know one particular device, that is the MOS transistor, and the way we know how it works is we apply a certain gate source voltage and the gate source voltage controls the drain current. This is how we have been discussing the model and operation of the MOS transistor. So, the first thing we will try to do is to bias it at a given gate source voltage and then apply an increment to the input, that is the gate source voltage, and see what happens. Okay. So, that is how we go about designing amplifiers, and it turns out that this type of thing will lead you to all the amplifiers, and then when one amplifier is not enough, you put multiple amplifiers together, you can do many interesting things with them. Okay. When we want to test a MOSFET or say its operation, this is what we do. We apply a certain VGS to the gate and apply a certain bias voltage to the drain. Okay. Now, in the initial part of the discussion, we can assume a sort of level 0 model where the MOSFET obeys square law and there is no channel length modulation. Okay. That is, in terms of small signal parameters, it is represented by GM and that is it. Okay. So, if I have a certain VGS, we will have a certain ID. The ID depends on both VGS and VDS. Okay. So, ID depends on both VGS and VDS, and we know how to calculate that. It comes from the square law equation. Let us say we apply a certain increment VGS to the gate. What happens to the drain current in this case? It will increase, and the incremental quantities are related by the incremental parameters or small signal parameters. So, this becomes ID plus GM times VGS. Okay. So, we have some response in the output current to an increment in the input or the gate source voltage. Okay. But let us say we want a voltage output, or we want to apply a voltage increment and sense a voltage increment. What can we do? We can try to pass the current through a resistor. Okay. So, this is a certain resistance RD. If we want to make sure that the operating point was the same as before, what do we need to do? In the quiescent condition, you get a drop IDRD, and across the drain and source I want VDS. So, this should be a larger value. So, the larger the value of RD, the larger this voltage needs to be. Okay. So, what will be the voltage across RD? When you apply the input increment, what happens to the voltage across RD? If it is defined in this direction, it is plus. Across the drain resistor, we have an increment of GM-RD times VGS, and the way to make an amplifier would be to make GM times RD more than 1. Okay. We will come to how we will actually isolate the increment from the bias point. For now, we assume that somehow across RD we have an incremental voltage, and under some conditions it can be larger than the input increment. Go on increasing the input increment, the size of the input increment VGS. What happens? Will the output increment go on increasing? We go out of saturation region. So far, we have assumed that the small signal picture or the incremental picture is this, right? In the incremental picture, the bias source VGS is grounded. We have this one and GM, and normally there would be GDS also, which we have ignored, RD, and the top of RD also goes to ground through the voltage source in the incremental picture. Okay. So, in triode region, two things happen. Firstly, the GM falls down and GDS increases. So, we had earlier made the assumption that all of this incremental current goes through RD. That will not be true in the triode region, and GM itself falls down. This is the reason why we would like to have amplifiers operating in saturation region. Okay. When I say GM is highest in the saturation region, I mean it is highest for that given bias current, given bias condition. Okay. And GDS is small. So, we would like to keep it in the saturation region. If VGS becomes large, positive, let me call this M1. M1 enters triode region where the behavior of the amplifier is not so good. Okay. So, what is the limit? What is the limit on the increment we can apply? How would we calculate that? VGD should be less than VT, right? Here we talk about the total VGD. This is not the incremental VGD, right? Or equivalently greater than VGS minus VT. Okay. So, what is the value of VGS that satisfies this equation? Please work it out and let me know. Yes. As I go on increasing the increment, the drain current will go on increasing. So, that means that the drain voltage will go on falling until it reaches VGS minus VT. Okay. Is it okay? So, what is this? This is really VDD minus IDRD is nothing but the quiescent drain source voltage. Okay. And VGS minus VT is nothing but the minimum value of the drain source voltage. Okay. So, you bias it at a certain quiescent value and there is a certain minimum value. So, it can go from the quiescent to the minimum. Okay. So, the output voltage can go from the quiescent value to the minimum possible value, which is VGS minus VT. That is the output divided by GMRD will be the input increment. Okay. Why do we get GMRD plus 1? So, the input itself is increasing, right. The input goes up and the output goes down. So, the point at which it enters triode region is different when the input is increased than when the input is 0. Okay. So, that is why we get GMRD plus 1, but you can see that for very large values of GMRD, you can neglect the 1. So, that means that the input signal is really small. So, this is the largest increment we can have, and within this increment, we sort of assume that it works as an amplifier, right. On the negative side, is there a limit? ID should not be negative. Yeah. So ID has to be positive. I mean, if you from an equation get ID to be negative, that's not really possible in reality. Okay. You are going outside the limits of the equations. So what's the value of VGS at ID by GM? Okay. This is the quiescent current divided by GM. So if you reduce the value of VGS, or if you apply a negative increment in VGS, then you will have zero current at some point. Okay. This you have to be a bit careful with. This is the ID versus VGS characteristics of the MOS transistor. Okay, and you bias it at a certain, let me call it VGS 0. Okay. Now, in the small signal model, what we assume is that around this point the current varies linearly, and the slope is the slope at this point. Okay. And the slope of this is GM. So this is the straight line from which we predict even large signal quantities like swing limits, like we are doing now. Okay. So this increment refers to this value. Okay. The current really goes to 0 only at this point, but we are not considering the actual parabolic characteristics of the MOSFET. We are considering the linear characteristics, assuming small signal increments. Okay. So there will be some error when you do this, but that is inevitable. For a single transistor amplifier like this, you can calculate exactly when it goes to 0. But when you have multiple transistor amplifiers, more complicated amplifiers, you can't do that. So you use this linear calculation as an estimate for when the transistor goes into cutoff. Okay. Is this clear? The point at which the current goes to 0 is this. The point we predicted is this one. Okay. That's because we have assumed that the characteristics will be a straight line with the slope evaluated at the operating point. Okay. For ID to go to 0, the VGS has to be VT. Okay. But we do all our calculations based on the small signal linear incremental results. Okay. So if you do apply the quiescent value of VGS minus ID by GM and measure the current in the MOSFET, it will not be 0. Okay. So this is an approximation we will use. Like I said, for more complicated amplifiers, it will be very hard to calculate the exact value at which it goes to 0. So that is one reason why we use the small signal approach. Okay. And the second reason is we are interested in amplifiers. That is, we want the output to be a linear function of the input or some multiple of the input. Now, as you can see in this case, the limit that you calculate is smaller than the actual limit. Okay. It's mainly because for more complicated amplifiers, we cannot calculate the exact nonlinearity that we do this, right? Now, the deviation from linearity is taken up in a separate case when we analyze distortion. Okay. So this behaves like an amplifier with the following limits. Okay. The incremental gain of the amplifier is GM times RD. Okay. What is GM in terms of its bias conditions? In terms of the quiescent current and the quiescent voltages? 2ID by VGS minus VT. Okay. And what is IDRD? It is the quiescent voltage drop across this resistor. Okay. I will call that VRD, okay, by VGS minus VT. This is nothing but quiescent drop across RD. Have you seen the gain of the amplifier in this form? What is interesting about this expression? It's actually not dependent on the GM or the MOSFET size or anything like that. Okay. If you want to get more gain, that means that you have to drop more voltage across the resistance. That is, you bias this at a certain VDS and you have a certain drop across RD. Okay. Now, once you have a certain drop across RD, you are limited to a certain gain. So, to get larger and larger gains, you have to increase the supply voltage. That's what it means. Okay. In this basic architecture, there are other architectures in which you can increase the gain, but this is one of the limitations that you have with lower voltage supplies. Okay. With low voltage supplies, you can only have small drop across RD. The interesting thing about this is it's not dependent on RD itself. You think that, oh, by increasing RD, I will make it larger. But then, if you increase RD too much, there will not be enough bias for the MOSFET. Okay. Then you will have to decrease ID. So, the bottom line is it depends on the product of ID and RD. So, you have to have a large voltage drop across the drain biasing resistor to get a large gain in this type of amplifier. Maybe I should redefine this. This is, I don't want to call this VDS plus IDRD throughout. This is what is called the supplier VDD. Okay. Now, what is the swing limit you see here? This is VDD, right, minus IDRD, which is related to the gain of the amplifier, isn't it? So, if you try to increase the gain, your swing limit will reduce. So, this comes out as a sort of fundamental relationship. If you want a larger gain, you have to have a larger drop across the drain resistance, and that's the only way to get larger gains. Okay. And what is this? Minus ID by GM. It's also minus half VGS minus VT, right? So, like I said earlier, when you apply a negative increment of VGS minus VT, the current goes to 0. But the linear analysis gives you VGS minus VT by 2. So, we made an amplifier. We haven't actually yet taken the signal part out. The signal is still across RD in this direction. Okay. That is why we get plus GMRD to be the gain. And we also know how to control the gain. We either have to increase the quiescent drop across RD or reduce the value of VGS minus VT. Okay. What is the consequence of reducing VGS minus VT? The FT of the transistor reduces, right? FT is directly proportional to VGS minus VT. So, if you try to get large gains by biasing it at a smaller VGS minus VT, you will end up with slower transistors, which is basically the same as saying the transistor gets longer or bigger or whatever. Okay. So, there is some trade-off between trying to get larger and larger gains from a single stage and getting higher and higher speeds. Okay. Right now, we have not evaluated the speed of this amplifier. So, I am talking about the intrinsic speed of the MOSFET. Okay. That reduces if you operate it at a smaller VGS minus VT. If you increase the drain resistor drop, supply voltage has to go up. If you decrease VGS minus VT, FT reduces, swing limit changes. Okay, actually in this case it's not a very useful conclusion, but the swing limit does change. Okay. Or in this particular case, if you increase VRD and don't increase the supply voltage, the swing falls. Okay. So these are general trade-offs that will appear repeatedly when you try to design amplifiers. Okay. I want to get only the incremental signal out. What can I do? Capacitor. So what's the condition under which I can use the capacitor? It has to be an AC increment, only then you can use a capacitor to block it. Across this we had the quiescent voltage plus GMVDS times RD. So across this, with respect to what we have called ground, we will have the quiescent VDS minus GMVGS RD. Okay. So to remove this part, what I really need is a battery whose value is VDD minus IDRD. Okay. Now I can't go around sticking batteries in series, and I don't know exactly what value it is either. So the trick that is used, that can be used under some conditions, is to first charge a capacitor to this voltage and then apply it in series. Okay. So instead of a battery, this is a capacitor charged to VDD minus IDRD. Okay. Now, if this is an infinitely large capacitor that can hold the charge for infinitely long, it will work for DC as well as AC. But because of the limitation on the size of the capacitor, it will discharge and it will work only for AC. Okay. So right now I have not connected anything on the right side of this, but presumably I will connect something here. Okay. Perhaps there is another resistor, or it could represent what is the input of the following stage. Okay. So under these conditions, what happens is, when in the quiescent condition, when there are no increments, the capacitor will get charged to VDD minus IDRD, and it will retain that voltage under what conditions? And if I apply increment, it should retain the same voltage, right? That's when I get only the increment out. So I want to get only the increment here, which is minus GMVGS RD. What's the condition for this to happen? The capacitor value is infinite, it will certainly work, because once charged has infinite amount of charge, so it will retain it forever. Okay. What happens if it's a finite capacitor? It will discharge. I am assuming that you are familiar with the calculation of the frequencies. So it will work only if the increment in VGS is above a certain frequency. That's dependent on the capacitance and the load resistance and so on. So I won't work it out here. You can go and revisit that thing. Okay. So similarly, I can do the same thing to add the input increment to the input bias. If I assume that the input increment is above a certain frequency, I know that the bias is at DC. So I can use a stage which passes the increment at high frequencies, that is beyond a certain range of frequencies, and includes the bias below a certain range of frequencies. Okay. And how do I do that? I use a similar network. I will have to have a certain source resistance here, and I have a capacitance, and I apply the increment VGS. Okay. Now, if this is at DC, it won't work. Okay. Only if it is beyond a certain frequency, it will work, and that frequency is related to the values of CS and RS. So, this is how you normally use this type of amplifier, but this is not the only way. I mean, you don't have to use capacitors, and we will see in IC design that frequently we don't use capacitors because capacitors occupy large areas and are hard to come by. So, if this particular amplifier works only if the frequency of the increment VGS is above a certain value. If that's the case, if the frequency of VGS is above a certain value, at those frequencies we assume CS to be a short and this maybe CL also to be a short. So, this circuit is more complicated than before. So, we will analyze this using the small signal incremental picture. Okay. The incremental picture simply gives you the increment and various parts of the circuit depending on the input increment, right. If I draw only the incremental part of it, I have VGS to be shorted. I have the control source GM. This RD is shorted at the top. The capacitor is shorted by assumption. And we may have an additional load resistance RL. Okay. And the voltage is taken with respect to what we have called the ground. In this particular case, it's the source of the MOSFET. Okay. So, what's the output voltage? GM times RD parallel RL. Okay. It's actually minus this times VGS. So, the sign is inverted because we take the output in the opposite sense compared to before. Okay. We take it between the drain and ground, not across the drain resistor. If you keep the same RD and include some RL, the gain reduces. Okay. So, this is also a general thing that if you include an additional load resistance, the gain tends to reduce. Okay. Now, it's also time that we added the full model of the MOSFET. So, the main thing that is missing here is the GDS. Okay. So, what's the gain in this case? Maybe I will write it in terms of conductances. It is GM divided by the sum of all conductances that appear at the output. Okay. And this naturally when GDS is very small compared to GD and GL, you can neglect it and you can use GM by GD plus GL. Okay. Yeah. So, under this condition, the gain is GM by GD plus GL. So, how would you increase the gain of this amplifier? Decreasing GD. Okay. So, that is one way. What else can you do? Increasing GM. How would you increase the GM? You bias it at a higher current or you use a larger MOSFET. Okay. So, to increase the gain, so let's assume that GD and GL are sort of fixed. They are loads that are given to you. Okay. So, you can either you increase the GM, and this can be done either by increasing the aspect ratio or increasing the quiescent drain current. Okay? So, either of these two will work. So, again let us take the opposite condition, and let us assume that somehow GD and GL are very small. We have not come across a case that works this way yet, but we will see that later. Okay. If GDS is much more than GD and GL, what happens? The gain is approximately minus GM by GDS. So, how will you increase the gain in this case? Reducing the current. Why does that work? What happens if you increase the current in this case? GM will increase, GDS will also increase. So, in this particular case, both of these are dependent on the bias point of the MOS transistor. Okay. So, if I write it in terms of currents, GM is okay, and what is GDS? Lambda ID. Okay. So, this is basically proportional to 1 over square root of ID. So, the gain actually falls if you increase ID. So, you have to operate at a smaller and smaller current to get better and better gains. Okay. Does it make sense? Similarly, what is lambda? I mean, what is the dependence of lambda on the parameters of the MOSFET? 1 by L. Okay. So, it is some k lambda by L. Okay. So, the gain can also be written as so you can either reduce the current or you can increase the size of the MOSFET to get more gain in this case. So, basically if there is no external load, if the external loads are negligible, the gain is given by the transconductance by the drain source conductance of the MOSFET. Now, this if you want to increase, you have to operate it at a small ID. Okay. Actually, this should be reformed and this will become clearer. So, I can write this as, these are some constants depending on the process. I will write it as square root of L divided by square root of ID by W. Okay. This ID by W we have encountered once before, I think, while discussing some assignment result or something of the sort. So, it is the current density per unit width of the MOSFET. So, to increase the gain of the amplifier when there is no external load, you have to either increase the length of the transistor or you have to reduce the current density in the MOS transistor. Okay. So, what is the consequence of either of these things? Increasing length will decrease the FT of the MOSFET, that is correct. What happens if you decrease the current density? So, the disadvantage of increasing the length is that the FT will reduce, and maybe because the inherent speed of the MOS transistor is reducing, if you make a complex amplifier using this, frequency response, the bandwidth of the amplifier also perhaps reduces. Okay. So, what happens if you reduce the current density? I mean, is there any disadvantage or is it okay to do that? Like, what happens to FT? Does it change or does it remain the same? Decreases. Yeah. So, it has the same effect, right? ID by W is mu Cox by 2L VGS minus VT square, and if you look at FT, it is mu times VGS minus VT by L square. Okay. So if you reduce this, keeping the length the same, that means VGS minus VT also reduces. Okay. So if VGS minus VT reduces, FT reduces. So it has the same effect. So in all cases, whether the load is dominated by external load or internal loads, we saw that the frequency response tends to worsen, meaning the inherent speed of the transistor has to be reduced to get more gain. Okay, that's what we have seen so far. So there is a direct trade-off between the gain that you can get in a given process and the bandwidth that you can get in the same process. Okay. Is this clear? So again, the amplifier is very familiar to you. What I wanted to discuss was more of trade-offs of this nature that you will come across, especially when doing an IC design. I mean, this is true even of discrete design, but if you get a discrete MOSFET, you have no way to change its width or length or anything of the sort, right? So in IC, you have freedom to do many things. That is, you can change its aspect ratio or you can change its operating point. So the job as an IC designer is to figure out how each of these things, the bias point as well as the aspect ratio, changes the performance of the amplifier. After that, you will be able to tailor your performance to whatever specifications you are given. Okay. Okay, let's continue tomorrow with this.